So we talked about this last class. This is the conceptual model for the Piedmont. I will ask you to draw this almost certainly at some point later in the class. So I did a video of this, drawing it out and explaining it, and it's available on campus now. Okay, so we talked last time about how wells are drilled, how they're created, the drilling process, the completion process, and now we want to talk about how we use them. And so I want to go through some nomenclature, some terms, and then give you like a conceptualization about how wells will work. We'll go and do some analysis of wells, but I think it's useful to start off with conceptual idea of how this process works. So we'll start out with these things: radius of influence and cone of depression, all that stuff. So I'm going to start out here drawing this out. There's the screen on the well and ground surface. Have it in a confined aquifer, and the initial heads will look like this. So when we pump water out of the well, what is often done is to have a pump that we put down low water level, down here, the screen. It's not always done that way. If the water table is shallow, then you can put a pump up here and lift the water up to the ground surface just by suction, like you lift water with a straw. Water out of the drink. If you're deeper than about 15 feet, though, that's not going to work, and you need a pump down here to push the water up. So got a pump down here, and start pumping, and pump the water out at a flow rate Q. Now, what that's going to do is cause the water level in the well to drop. And then we've got a gradient between the water, between the hydraulic head in the aquifer and the hydraulic head in the well. So the hydraulic head in the aquifer then is going to look like this. So it's dropping by that much. And we call that change in head the drawdown. And we pump out, running a little bit longer, water level drops to here, and then we've got drawdown like that. So we see that the well is causing drawdown out to a distance here, but out beyond that distance, there really is no effect. There's no change in the water level. So this is the radius of influence. That's going to change with time. So radius of influence will increase. So the drawdown, we'll call that delta P. You see different terms for it, but I'll call it delta P. The change in the change in the head, or the drop in. So the head is decreasing, but the drawdown is increasing. The drawdown is that's positive. And we'll also be interested in the drawdown in the well. So that called delta TW, the drawdown in the well. Now, this is symmetric around the well. So the drawdown is going to look like this. At this time. And you can imagine that if we revolve this around the well, then we've got the hydraulic head forming a surface that looks like this, right? It looks kind of like the bell on a trumpet. And that has a cone shape. So this thing is called the cone of pressure. So that's the overall region around the well where the drawdown has occurred. Okay, so we're pumping water out at this rate, and that pumping action causes drawdown in the well. The ratio of the flow rate coming out of the well to the drawdown in the well, that's the specific capacity. We pump the well long enough and it goes to steady state, that means that the drawdown isn't changing anymore. And so the flow rate, if we're pumping at a constant rate and we pump this well long enough so that we reach steady conditions, if that happens, doesn't always happen, but if it does, then the drawdown is now steady. And this is then a constant. It is one of the measures that's used to describe the performance of a well. We're going to be interested in how rapidly we can pump water out of the well. That'll be important. But the harder we pump it, the higher this is, the more drawdown that we're going to cause. And these two are related in this ratio. At steady state anyway, this ratio is a constant. So if we double the flow rate, we'll double the drawdown. So that's going to be important because there's a pump down here. And this is the drawdown in the well. You know, if the drawdown in the well gets to here, pump doesn't have any water to pump. And a lot of times the pumps that we use are electrical centrifugal pumps. They spin around real fast with electric motor, and if they don't have water coming into them, that motor doesn't get cool and they burn up. So increasing this causes that to increase, and ultimately we're going to hit a limit that will damage the pump. And so there'll be a limit to the drawdown that we can have. That'll limit the flow rate through this specific capacity. Another combination of terms that we're going to be interested in is how much power do we have to have?
How the drawdown is different from the drawdown on the well, because they have like different notation, like delta P and delta PW.
Delta P is the drawdown anywhere.
Okay.
And delta PW is just the drawdown in the well, specifically at that location. Okay. So this is going to be, generally, this is an electric motor, and we have to give it some power, and we want to be able to calculate how much power we have to give it. So this pump has to move water at this flow rate, and it has to lift it from here up to the ground surface. Okay, and the higher it has to lift, that requires more power. The bigger the rate is gonna increase the power. So the power is gonna be proportional to the flow rate and the drawdown in the well. And we'll multiply that by the unit weight of water. That gives us units of power. This drawdown, we would also add in that distance to give us the total amount that we have to lift. This ends up being important because if you have a very deep well, then you start to have significant amounts of drawdown that can then increase the power that is required. And if you have a deep well, maybe eventually the drawdown is high enough so you can't even lift the water out of the well. Okay, so those are some basic concepts and terminology. We have another monitoring well out here, doesn't have a pump in it, but what's going to happen is the water level is going to be equal to the head at that point. And this, putting in a well like this, a monitoring well, that's going to be how we determine what the head is here and what the drawdown is. And then measurements of the head and the drawdown will be what we use to analyze how the well is performing. Okay, so here are, this is function of the cube, radius of influence. One thing too that I have here, this is then a contour map in view. And this shows the cone of depression. And one thing we wanted to point out here is if we draw this with flow lines in it, and we have flow that comes in like that, and flow that comes in like that, and they're perpendicular, right? Because we're assuming that it's isotropic. And what you get from this is that in order to have the ratios stay the same, this is now a flow net. And in order to have that ratio stay the same, the spacing between the contours has to decrease as the well is approached. Hopefully, on the flow nets that you handed in, that will be one of the characteristics that you found, that this spacing has to decrease as you get closer to the well. The hydraulic head in the vicinity of a well at steady state, just the kind of a basic analysis gives you that the hydraulic head varies as the natural log of radius, the radial distance. So natural log looks like that, right? And kind of keeps on going. So that is the function that describes the hydraulic head in the vicinity of a well. So take that and revolve it around. Here is a plot of what that looks like. So that's the log function. And we just revolve it around. Okay, so that's kind of a basic look at what the cone depression should look Okay, so we've got a couple of ways of looking at well performance. One thing that we might want to do is predict the drawdown or the flow rate. Yeah, I mean,
The unit of the specific capacity.
specific capacity. Well, the way you can think about it is it's the flow rate out of the well that you get per unit of drawdown. So this is a volumetric rate. Q is volume per time. And that is per unit of drawdown. So it's going to have units of length squared per time, same as transmissivity. Yep. So we want to be able to, here are a couple of things that we want to, kind of a couple of perspectives on how we're going to use wells and assess well performance. So one thing that we might want to be able to do is predict the drawdown or the flow rate from the well. We want to use it to recover water. We want to know what the flow rate that we could pump is. And if we do pump it at that rate, at that rate, then what is the drawdown? So in order to do this, we need to know the aquifer properties. And when we do this, we can use that calculation for well design. If we wanted to use the well for dewatering, then we can use this kind of calculation to evaluate what would happen. Another thing that we can do, though, is that the drawdown the drawdown for a certain amount of pumping depends on the aquifer properties. So if we know the drawdown and we know what the flow rate is, then we can use the measurements of drawdown to estimate what the aquifer properties are. So this is how we're going to characterize aquifer properties. This is the procedure for calculating the transmissivity and hydraulic conductivity and storativity of aquifers. We're going to pump the well. We're going to cause drawdown. We're going to measure the drawdown, and then we're going to analyze that drawdown. Okay, so these two are hydraulic aspects. They're related to the flow and the drawdown. Another thing that we're going to want to know is what's the capture zone of the well. And the capture zone is the region where water that recharges an aquifer ends up going to a particular well. When we did that contour exercise in class, we drew out the capture zone of the well just by graphical construction. So we'll also want to be able to calculate that. Okay, so here's some results from a GMS model. And this shows kind of a basic behavior of what happens when a well is pumped. So there's the well, and I have a monitoring well right there. And so I'm going to start pumping, and the drawdown in the monitoring well is shown here. This is a time series of drawdown as a function of time. And this is a map view. So this is a stream right here. And the boundaries that I have here are just, these are not actual boundaries. The model extends long distance in this direction, and down there. Okay, so we start pumping, and this is time 001. We don't care about the units at this point. See a little bit of drawdown here, and not really showing up here. So now we pump a little bit more, and you can see this grid. You can see these little squares. This is from the grid that you saw when you did the models for the flow nets. And the hydraulic head is now dropped in this area and the drawdown has increased. So this is 0.01 and in the time series, it's right here. You can see now we have a little bit of drawdown. We're measuring it right there, so you can see it's a little bit of light blue. All right, so we continue to pump. This radius of influence expands. This is the cone of depression here. See how those contours, it's kind of blocky because of how the contour is drawn, but these should be circular. But you can see how the spacing is increasing or decreasing as you approach the well. This is starting to light up, so we're having more drawdown, and at time 0.1, you can see now the drawdown is here. So the drawdown is increasing as the water level is dropping. This is pretty much a circle at this point. So we have, I think, pretty good axial symmetry around that point. So another 10 units in time. This is a time equal to 1. Maybe one hour or 1 day or 1 year. Doesn't matter at this point. But what we can see is the circle is expanding and the drawdown is increasing, and we're going up here along this point. And one thing that we start to notice here is that this part of the curve is straight. So we start out and it's curving up, and then when we're in this part, between like 0.1 and 1 and maybe a little bit later, this is straight. So this is a log axis. And so when you have a function that plots as a straight line on a semi-log axis like this, then that means that it's a logarithmic function of time. Okay, now that's a characteristic behavior of the drawdown in the vicinity of a well that is in an infinite medium. So this aquifer, for all this well knows, this aquifer extends out to infinity. And the response that is occurring then is the drawdown is changing with time, and it's a logarithmic function of time, and that shows up as a straight line, a semi-log straight line. Okay. All right, well, that's about to change because the aquifer, no aquifers are infinite extent. There's always some boundary. And in this case, we have a boundary over on the left side that's a stream. And we're assuming that stream is cutting through the aquifer. And so the stream is causing the head in the aquifer to be equal to the head of the stream. So it's a constant head boundary. So here's what happens in the next leg of time. You can see now this red line on my screen. It's pretty clearly not circular anymore. Does it look like that to you? This is getting kind of flattened, and that distance is shorter than that distance. So what's happening is this is a constant head boundary. So the head here cannot change. So this is a little bit of drawdown, and you're just not, this isn't going to be able to go over to that boundary. So it's getting suppressed a little bit. Water, what's happening is water is coming out of storage here because we're dropping the head. But when the drawdown starts to approach here, we're going to have water coming out of this boundary and flowing towards the well. And what you can see what's happening here is if we extend this straight line out, at this point, time equals 2.4, we're starting to curve and drop off of the projection of the semi-log straight line. So we keep going in time. You see this flattens out even more and extends out in this direction. And this flattens out even more. And then we go out in time yet. And this is flattening out even more. In fact, this looks like it is flattened out and the slope is essentially zero. So if the slope is zero, that means that the drawdown is not changing with time. And that's the definition of steady state. Okay, so right in here, the well is progressing, we're pumping water out and the drawdown is increasing. But and that's not steady state because the drawdown is continuing to increase. But now here we've reached what looks like it could be steady state. We probably want to go a little bit longer and see if it really is flattened out. Okay, so there we have just the conceptual. Well, it's actually a model, so this is really numerically accurate, but this is showing some of the aspects that occur as you pump a well that's near a boundary. So let's take a look at what's happening here conceptually. So here's the well and here's the initial heads. So we start pumping and we get drawdown, much like I drew a few minutes ago. When we go from here to here, that's been a unit in time. And during that unit in time, we've been pumping at this constant rate. And we've produced a unit volume of water. Okay, so that water has been released from storage over this time period. So the volume that has come out of the well while we pumped it, that volume was stored in the aquifer and now it's no longer stored. We've removed it. So back when we were talking about storativity, we were saying, well, storativity is the volume of water released from storage per unit area per drop in head. And the reason we kind of cast it in that framework is because of this. But here, with this pump, we're dropping the head and we're moving water from storage. And the specific storage or the storativity could be what tells us what happened. So the volume that is released from storage. Remember, we said that the storativity is equal to the volume released from storage per area per change in head, right? So the volume released from storage, we can bring this stuff over here, and that's what I did. Okay, now that's delta H bar. So that's the average change in head. So here, this head has changed. The head change differs within the radius of influence. But if we went and averaged that out, it would be like that. That's the average head change. So the volume that we've pumped out, we were able to do it because we're dropping the head, and the amount that we get out is that. Storativity times the area. And the area is this cone of depression. So go out that radial distance, and that determines what the area is. Okay, so that's being released from storage. And then we do it again. And so this is changing. The region that we have affected is changing. So the volume released from storage is this. And we have area is increasing and the delta H, both of these are increasing. The drawdown is increasing with time, and we're influencing a bigger area. Okay, so both of those things are changing. there's the radius of influence that will determine the area. Okay, so the volume that's released from storage, that is changing as a function of time by the pumping rate. So what I did was just take so if this is the volume of water released from storage, and take the derivative of that, at flow rate. And if we take the derivative of this, and at this point, we just fix the area. So we hold the area constant, and we see then that the flow rate is just going to be equal to the negative of the head change with time. Okay, the head is dropping, and that's releasing water from storage. So when this is positive, that has to be negative, and the minus sign then flips the sign. So that side is positive. So we drop the head, we produce water from the well. So we see that the head in the well is going to be dropping. So the head of the well drops with time. And if this is also increasing with time, then this can decrease. This is the slope of this line, right? The rate of change of head with time. That's this slope. So if the area that's affected gets bigger as we pump, the rate at which the head needs to drop can diminish. So this starts out steep. We have to drop the head rapidly at first, but then the more we pump, the bigger this area gets. And if we're affecting a very large area, then we only need to drop the average head over that area by a small amount compared to when we're affecting just a much smaller area. Okay, so as the radius of influence increases, this slope can flatten out. So that gives us a curve that looks like that. It's qualitative. It's decreasing to release the water from storage, and the slope of it is flattening out because the area is getting bigger. Okay, see how that works? Yeah. Yeah. Okay. So the drawdown then is this is going negative. The head is dropping, but then the drawdown is the flip side, or change the sign. So it's just the same function, but it's flipped like that. The drawdown is increasing. So the drawdown curve as a function of time looks like that. That's what we're expecting. We haven't done any analysis yet, but that's qualitatively what we expect this to look like. One of the things that we see too is that there's no steady state. In order to get water out of the well, we have to remove it from storage, and we have to have a drawdown change with time. So this is continuously dropping, and this is continuously rising. Now, we see wells that go to steady state. That happens, it's pretty common. So for shallow wells. So here's an explanation for how that can happen. You start pumping water out of a well, and at this point, things are just exactly the same as they were. And same as this, we have the same response that we had with the previous case. And even right now, the same response. But in this case, we have a stream right here. And when the drawdown cone reaches the stream, then the drawdown will start to change. Because when we go from this point, okay, so there's the drawdown for basically the case we saw in the previous slide. But now when we go take the next step, come on, there you go. So when we go here, this is a constant head boundary. So you can't have this drawdown happen. This is going to cause the head to stay not there, but up here. And this gradient will cause water to flow out of the stream into the aquifer. So instead of producing water from releasing it from storage, you can produce water by taking it out of the stream. Okay, so that means that we no longer have to have more drawdown with time to progressively release more water from storage. We can get it released from the stream. So that causes the head to flatten out like that, and the drawdown to flatten, and that allows us to go to steady state. So interacting with the stream is a way that wells can go to steady state. Steady state is possible. UT is 0. So here's an example of that, where these heads flatten out as a function of time. So here's a simple analysis of the hydraulic head as a function of radial distance. This is called the time equation. And this was the first equation for the hydraulic head, the vicinity of a well. This is steady state, and what we're assuming is that water is being pumped out of the well, and that we know what the radius of influence is, and we can use that in the equation there. So this is the flow rate, transmissivity of the aquifer, and that's the radius of influence of the cone of depression. So if we know that, then we get this as the function that describes the drawdown cone. Awesome. So what I've been drawing so far has the hydraulic head starting out as flat. And that essentially, conceptually, you can think of that as the initial conditions, and what we're drawing then is a departure from the initial conditions. But really, the hydraulic heads are not going to be flat in most practical cases. They're going to start out with, will be some kind of hydraulic gradient. And here's an example. So here's two streams, and there's recharge. And you solve this problem for homework, right? The hydraulic heads between two streams with recharge looks like that. So it's doming up, there's the divide. And we have flow to that stream and flow to that stream. Now, if we have a well right here, what's going to happen is the drawdown that I was drawing relative to a flat initial condition is going to be superimposed on this curved initial head. Okay, so after an increment in time, the drawdown now looks like that. And we have another little increment in time. And what we can see now, the hydraulic head looks like this. There's the divide. So recharge that comes into the aquifer on this side of the divide goes to the well. Recharge that comes in over here still is going to the stream. So at this point, though, you can see that the gradient, the hydraulic gradient here at the stream has changed. So the well has started to influence the stream, but it's not actually removing water from the stream. It's just, what it's doing is capturing recharge that would otherwise go to the stream. So the stream will have less water in it, but it's not because the well removed the water, it's because it captured water that would have otherwise gone to the stream. Okay, now that's going to be important because as we continue to pump, you can see as we get more drawdown, right there, the gradient is about flat, but we keep going, and now we have a gradient that would be pulling water out of the stream. So in this case, water is actually physically flowing out of the stream over to the well. That is going to have a big, but that could have potentially big consequence because at this point, none of the water that's coming out of the well was in the stream, but here it is. And if the water in the stream is contaminated, then that water is entering the aquifer and can end up as well. In these other cases, it's not. Okay, so there's some important distinction there. One of the things too that can happen is that streams are lined with lower permeability material. There's some lower permeability material in the stream bed that tends to disconnect the stream from the aquifer. And here's an example of the heads that occur when that happens. And what you see is that the drawdown from the well can extend underneath the stream, and you could have an effect of the well over here on the other side of the stream. So in a very idealized case, the stream acts like a constant head boundary, so the head change from the well can't make it past the stream. But in reality, it can. And it could do that because of low permeability material on the stream bed, or it could do it just because of low permeability here between the aquifer and the stream. Okay, so wells can go and affect the ground on the other side of the stream. All right, let me just end with one last concept, and that's the capture zone of a well. So here's just a simple example. These are some flow lines and equipotentials. And what we're interested in is the region where recharge would end up going to the well. So this right here is the radius of influence. So this is the region where you have drawdown caused by the well. But you can see that the water that recharges the aquifer at this point is going to end up being captured by the well from these streamlines. So the capture zone for this well is much different than the radius of influence. Out here, the well is changing the head in the aquifer, but it's not capturing the water there. So if you were looking at if you had a monitoring well here, you would see when this well was activated, there would be drawdown. But it's not enough drawdown to capture this regional flow. So these concepts of radius of influence and capture zone both indicate what the well is doing to its surroundings. But one of them is an effect on the hydraulic head, and one of them is an effect on the contaminants or where the water that the well is producing coming from. So if you do more sophisticated models, you can do capture zone analyses. That ends up being a big part of protecting water supply wells. And here's an example of capture zone of a well. And here's some other examples done with, this was done with GMS. So this will all be stuff that we'll be able to do as we build our GMS skills. Well, okay, very good. Well, have a good break, and I'll see you on Wednesday. I'll have that exam on Friday.